Okay, for today's class, we're going to cover chapter 29, sections 4 through 6, and we don't have any concept questions today, but we're going to cover these exercises. So go read these sections and prepare yourself to apply those concepts to these problems and come utilize the video for guidance. Okay, starting with number 11. Number 11. Okay, so what we have is we have a loop. We have a loop, and we're told that the magnetic field at the center of this loop is 2.5 millitesla. Okay, so we have B at the center of this loop. Okay, we're told the radius of the loop, so we have B at the middle, we're given R. The question is, what is the current through the loop? Okay. So what are we going to apply to find that? How is the current related to the B field and the radius of this loop? All right, well, we know that the B field at the center of a loop is mu naught I over 2R. Okay, mu naught I over 2R. And so since we know what the radius of this loop is, we know the B field, we can solve for I. And by plugging in our numbers, you'll get I is about 20 amps, 19.9 amps or 20 amps. Okay. So again, this is practicing with the relationship, recognizing that I can use this for this case because this is at the center of the loop, and this is the equation for the B field at the center of a loop. Now we have other geometries, and you have to make sure you keep them straight. Okay, now part B says, well, what if you had this much current, the current you found, flowing through a wire? Okay, at what distance from that wire would you get the same magnetic field you got in this case? So what equation, what relationship are we going to apply here? Okay, so we have B for a wire, a long straight wire, is mu naught I over 2 pi R. Or maybe I should do lowercase r here because it's distance away, where maybe I should have done a big R here because that's usually utilized for a radius. Okay, so this B is the same B as this one. Okay, this I is the same I as this one. So the question is, what is this R? And if we divide these two out, we're going to end up with an equation that says, come down here, that says that this distance is big R divided by pi. If you divide the top one from the bottom one, so it's kind of an inverted divide, the B's cancel, mu naughts cancel, the 2's cancel, the I's cancel, and you're just left with a pi over the big R to equal this R. By doing that, you'll end up with 1.6 millimeters. Okay. Another way to do that is just take this number, plug it in here, take this number, plug it in here, and solve for this R. Okay, now number 13. Okay, so on 13, we have this configuration. We have wires that are all identical. Okay, we have current flowing into that junction from this side, and we're asked what is the field right there, the magnetic field. What do you think? First of all, you should probably ask, well, what's happening in current when it gets here? If these are all identical, it means half the current flows this way, and half the current must flow this way. Okay. Well, now I have some current carrying wires that are near a spot where I'm trying to find the magnetic field. So with that in mind, what's the magnetic field here? But think symmetry and think about the position dependence of the magnetic field equation. Okay, this current is flowing directly towards that point, which means the R is this direction. And they're parallel, which means this creates no magnetic field there. The fields are looping around this, but they're not in front of it or behind it. So this doesn't do anything here. Now this one flowing up, it ought to create something there. You know, it's flowing upward, and so it should be down into the page there. But this one's flowing downward. And if it's downward, I'm going over here, then it should be coming up from the page there. So this creates no field there because it's pointing straight at it. These two cancel each other's fields there because they're in opposite directions and the distance is the same direction. So there's two reasons why B equals 0 there. Okay? Two very important and very distinct reasons. Okay, number 15. This one has a bit of good review in it. Okay, so we've got a battery, applying current to 3 resistors called R1, R2, and R3, and this is delta V battery. Okay, delta V battery. And we're asked, what is the direction and magnitude of the magnetic field at this location A, which is a distance of 2 millimeters up from this wire here. So far away from all the other wires, but 2 millimeters up from here. Okay. How do we find that out? How do we find the direction of the magnetic field at that point? Well, first we have to think about where direction the current's going. So if I think about this as a circuit, this potential of the battery is across from here to here. And so this whole path has a potential difference equal to the battery. The positive side's over here, which means current ought to be flowing that way. The current's going to be flowing to the left in that wire, which if that's the case, and by the right-hand rule, current to the left, R up, it means that the magnetic field is down. Okay, you can curl your fingers, thumbs that way, fingers curled down in the page at the top. So that is into the page. Okay, now how big is it? Well, it all depends on how big this current is. Because we have the equation for a wire already, we just need to know how big that current is. Well, that's going to be from Ohm's law, through 2 resistors acting in series. Now, they're also acting in parallel with this one, but I don't care about this one because I already have these resistances, and I already have the potential across them, and that's sufficient for me to find the current. So I can find the current through Ohm's law by saying that's equal to delta V over the equivalent resistance, which is R2 plus R1, because they're in series, or 3, R2 plus R3, they're in series. Okay. And if you do that, you'll get 6/5 amps, which then if you plug into this equation, you have B equals mu naught I for 2 pi R, and plug in all those numbers, you'll get 0.12 millitesla. Okay. All right. Continuing practicing with these equations. So now we're going to move to problem 20, and this is focusing on line integration. Okay. So we have this set up here. We're going to go along the line from the origin to this spot here. That's our final spot. Here's our initial spot. And these are in centimeters, 50 centimeters this way, 50 centimeters up. Okay. And we want to find out what the line integral of B dot ds is from that initial spot to that final spot. That's what we want to find. So when it says what is the line integral, that's the line integral. Okay. Now the thing that's important here is that our magnetic fields everywhere in this space are pointing along the line. So what is the line integral? Well, being pointed along the line means that they're parallel to each other. The path, B field is parallel to the path, and so the dot product gives me a 1, cosine of 0, because they're same direction, gives me 1. The B field's constant, and so this just becomes B times L, whatever that length is, which we can calculate being the hypotenuse of a 45 right triangle. And when you plug in your numbers there, you're going to end up with 0.0707 Tesla meters. Okay, Tesla meters. It's B field times length. Okay, this is pretty small. This is 0.707. Pretty small line integral. It's a small magnetic field, and the path isn't huge. Okay, so going further now, let's do number 21 and apply the same ideas. Okay, in this case, the same path, exactly same path, only now we're in a region of space where the magnetic field is pointing perpendicular to the path. So what is the line integral? The line integral is 0. B dot ds is 0 because, not because b is 0, that's definitely not 0, not because ds is 0, it's because they're perpendicular to each other. So the dot product kills it, because that would be cosine of 90 degrees, which is 0. So it's 0 because the path is perpendicular to the B field. Okay, now 23. At 23, we now get to apply this line integral stuff to Ampere's law, which says the closed line integral of B dot ds is equal to mu naught I enclosed. Okay. So in this particular system, we've got 4 currents coming in or out of the page. We have one current here that's going into the page, one current here that's coming out of the page, one current here, we don't know what it's doing. It's either in or out. And one current here that is going into the page. This would be I1, I2, I3, and I4. And our question is to find out what is the current through 3, direction and magnitude. If we know that on this very weird looking path, going clockwise along that path, we know that the line integral along that path is 1.38 times 10 to the negative 5 Tesla meters. So we have a number for this. We're told what that is. Okay, so we know what that is. What is the current through I3? Okay, well, that's going to equal mu naught I enclosed. And the question really is, what is I enclosed in this case? I enclosed means currents that pierce through the loop, that go through the loop. So is I1 enclosed? Nope, it's outside the loop. Is I4 enclosed? Nope, it's outside the loop. Which is really amazing that this works even if there's currents close by. If they're not through that loop, then they don't contribute to this line integral. It's only dependent on the current through that loop. It's an amazing conclusion. Okay, so what is enclosed? Well, we have mu naught. We have I. Now here we have to be careful about direction. This direction gives us that value that I quoted, and we need to choose by the right-hand rule a direction that's consistent with this in terms of positive. So if it's clockwise, then we choose into the page, because my fingers are going clockwise, so my thumb goes into the page. We choose that to be positive, and then out of the page, like I2, would be negative. So your path direction defines your positive, and then you choose your signs accordingly. So our path is clockwise, so that's a positive path, which means down into the page is positive by the right-hand rule. So I don't know what I3 is, but I'm pretty confident it has to be positive, because if this is negative and I get a positive number for this direction, that must be greater than minus I2, because that was negative, because it's going out of the page. And then solving for I3, you get I3 equals the line integral, which I'm just going to briefly say that, plus I2. And if you plug in your numbers, I kind of run out of room, plug in your numbers, you're going to get 23 amps, which is a pretty big current. That's a pretty large current. But given that the other currents are 12 amps, 18 amps, 20 amps, it seems consistent with those values. Okay, last one, 24. This is, again, mostly conceptual, this problem, but it's really trying to understand what line integrals are and how B fields work. For this problem, we have a path. This is just a path. It's not a wire. It looks like a wire, but it's not. It's just a path. Path through space. There's nothing physically there. And I have a wire here that's going into the page with a current of 2 amps. The radius of this bend in this path is given. We call that R. And then the length from this initial spot to this final spot is also given. Okay, so we know that length. So the question is, what is the line integral from initial to final? What is, and this is not closed, this is open, B dot ds along that whole path from initial to final? Okay. Think carefully about this. How do you utilize this line integral? Okay, think about the field of this current. We know it's circular around it. It's going into the page, which means those circles are clockwise. And so at a distance r away, the field is pointing tangent to that path. Well, what direction is the field right here? It is straight up. Okay. And right here, it's also straight up. It's straight up everywhere along this line that emanates straight out from the wire, because the fields curl around the wire. Same reasoning says that it's straight down over here. So along this length of this path, what is B dot ds? It's 0, not because B's 0, B's not 0, not because the length is 0, we're moving along some distance. It's because they're perpendicular, and the dot product only cares about how much is parallel. So because of that dot product, this line integral is 0 for this point, and the same reasoning, it's 0 along that. So all I care about is this half circle, the semicircular arch. So this reduces, if I call this A and this B, this reduces to A to B of B ds. With no dot product, because they're parallel to each other, and so the dot product just gave me a 1. That just becomes then B is constant, since it's a constant distance away, times ds integrated from A to B, which is a half circle, so that's pi r. Okay, and so this line integral is just B times pi r. Now, that is a wire, a straight wire, coming in and out, and I have an equation for a straight wire. So that's going to be equal to mu naught I over 2 pi r times pi r. So this is B, and then I multiply by the pi r. Pi r's cancel, and I just have mu naught I over 2. Now, that's a pretty slick result, but it came about because we are careful to think about all the important features of directions of B fields and how this line integral works with that dot product. So finally, plug in your numbers. If you plug in the numbers, which they're all given, it's 1.3 times 10 to the negative 6 Tesla meters.